I'm able to kind of make it work, but it might not work every day, you know. So anyway, today, so if we keep going with the class notes, I think it should be page, for me, 53. What should this be? Lecture 9. ES 305. February 13, 18. Okay, so let's see, what did we do the other day? So let's do a quick review. So I think last day we did some problems, and basically I was showing you that the change in internal energy is proportional to what? M CV delta T. Okay? Then we defined something that was called the enthalpy. Which is defined as what? Internal energy plus work done by the pressure. And we say that the change in enthalpy will be proportional to what? M Cp delta T. So notice that one change in internal energy is related to delta U. Change in enthalpy is related to Cp. Okay? So basically in this one we say that, trying to give an explanation, but this one would just be like you have a closed system. What is the change in internal energy within the system? Okay? And that the delta H, in addition to take into consideration the change done within the system, we also take into consideration what? The work done by the pressure. All right, so let me give you some relations. So this will be relations. You can add two units sheet that you can take in the exams. All right, so those relations, let me go find them on the book. So we are on chapter 3. So I'll see if I can find them here. This relation between CPs and CVs. So basically, we have been talking about CPs and CV, and gamma is defined as, so what was gamma? Do you remember gamma? We say different gases have different compression ratios, no? Okay? So the real definition of the gamma is CV over CP, or vice versa. Let's find out. So these different relations then that relate. So CV, I told you the definition is change in internal energy in function of temperature and constant volume. Delta H is change in internal energy with respect to temperature at constant pressure. So for incompressible, you have Cp equal to Cv. But page down. Let's see if we find the relation for compressible. There we go. Page down maybe will work better. Okay, what are the relations? Is this not showing the whole page? Or? Okay, there we go. All right, so it's actually reversed. So let me come here to, oh, I don't have to do that. So let me remove this. And let's see if I can do this over here. Maybe I can do the other side, maybe better. All right. So basically, gamma, which is the gas constant. All right, so in the relation, for example, on the relation we have what? PV to the gamma equal to a constant for what type of process is this one called? Polytropic process, no? So you have a different gamma for different gases because different gases might compress differently, okay? So that gamma, which in the book is called K, as you can see, is defined as being equal to what? Cp over C sub V. Okay? And now this other relation, so this is, so we can write here 4 for incompressible gases substances. What do you have? You have Cp will be equal to Cv. So basically this implies what? Gamma is equal to 1, okay? For some compressible gases, substances, we might need these relations or not, but I give them to you, is we have Cp is equal to Cv, C sub V plus R. Okay, so if we combine this equation here with this equation here, you can actually show that what? Cp, C sub P is equal to gamma R divided by gamma minus 1. And that C sub V will be equal to gamma divided by gamma minus 1. No, it's both are gamma minus 1. If you look at it, I'm just copying this relation from here, okay? Their K on the books is our gamma. Okay, so this relation, I mean, there's nothing to derive, so I'm not going to ask you to memorize them. I think that learning is understanding, and there's nothing in understanding in memorizing, no? So these relations here, you can see like gamma equals Cp over Cv, Cp equals Cv plus R, and these two relations over here. You are more than welcome to add them to the unit sheet that you can bring to class and to the exam and put it over there, okay? Again, I'm not going to test you in memory. I'll test you in understanding. Yes?
On the 347B, is that the one that you were doing for CV? It's got R on top.
Yeah, but what I'm saying is that you see on the book is K, no?
Right.
Okay. the K and the Clasnos is our gamma.
Well, I mean the one below that because it's got an R.
Oh, it's R. Oh, C for CV. No, you're right. C. So you're completely right. So this one is, instead of gamma, is R. Yeah, sorry for that. Thank you. Okay, most important here is that really you realize what? Is that you see here that the change in internal energy is proportional to what? CV dt, no? Okay? That's really the part that I want you to understand. And the HT is equal to what? The integral of Cp dt. Okay? That's the important part for the understanding. This is a matter to know these relations, okay? In case you need to use them in a problem. All right? So let's do problems. Let's see what we can do. So let me magnify this for a second. And let's try to find problems on chapter 3. Oops, I think I went a little bit fast here. So what is the highest number we did as the homework problem so far? 56, okay. Okay, 389 is a classic one for something different. Okay, let's do 385, okay? I like the one with pictures, okay? I don't know why, but. So 385. Let's see what that problem is about. So page 54. So we're gonna do problems 385. Okay, so let me see if I can do this again here. I'm gonna minimize the bottom. Oops, that's not what I wanted to do. You see what I mean? I wanted to make it a bit here shorter, but a bit wider. There you go. Okay, so that way we can have the problem statement and my page. Okay, so as shown in figure 385. So let me do a little sketch here of figure 385. Okay, remember all this is part of the solution of the problem. Okay, so our system here is this one over here. M equal half a kilogram, and what is the substance? Ammonia. Okay, looks like to the ammonia they're gonna add some heat Q, and that we know that initially we have T1 equals to minus 20 degrees Celsius and X1 equals to 25%, sorry. So what is the state of the ammonia? So it would be a mixture as state 1, no? Yeah? Then at the end, they give us that T2 is equal to 20 degrees Celsius and P2 equal to 0.6 megapascals. Okay, so let me start reading the problem. So as shown in figure 385, half kilogram of ammonia is contained in a piston cylinder assembly. initially at T1 minus 20 degrees Celsius and a quality of 25%. As the ammonia is slowly heated to a final state where T2 equals 20 degrees Celsius, P2 equals 0.6 megapascal. Its pressure varies linearly with specific volume. Okay, so what does that mean? What does that mean, mathematically speaking? P equal what? Let's say to a constant times V, no? Yeah, vary linearly, so this will be okay, where C will be a constant, which I guess we don't know. There are no significant kinetic and potential energy effects. So we can put over here, change in kinetic energy equal to change in potential energy equal to 0. Okay? For the ammonia, show the process on a sketch of the PV diagram. So that's good because no matter what, you need to do a diagram, no? So let's say we have here a PV diagram. So on the PV diagram, what is constant? We need lines of constant temperature, no? Okay, so I mean, I can probably sketch one now, but maybe the picture is not going to be pretty. But let's just do one now, okay? So let's say we have here. So let's say this one is T2 equals to 20 degrees Celsius. And this one here, again, can I just change it here? If I need to change the figure, I will change it, but T1 equal to minus 20 degrees Celsius, no? So what should be our state 1? We know we are minus 20, so lines of constant temperature, and we know we need to be in this region, no? Of the mixture. So let's say we are somewhere over here. Yeah? So this is V1, I'm guessing. Okay, so what is the second thing we need to do? Evaluate the work and heat transfer each in kilojoules. So we need to find Q over here. And the work, each one in kilojoules. Okay, so maybe over here, oops, sorry. Let's start by what we have, okay? To tell you the truth, I don't know exactly how to do this problem yet, but as we move ahead, we find the solution, no? Yes?
If P varies linearly with respect to the specific volume, would the PV diagram just be like a straight line and not a curve?
This is the pressure. Maybe what the line, when the pressure will vary P1 to P2 might be a straight line, yes. Okay. We probably do a straight line, okay? So if you want, what I'm thinking now is that we know P1, we can find V1, no? Then we know P2, we can probably find V2. And if we know, and then we can write P1 equal P2, so C1 equals C1, V1 CV1 equals CV2, no? And we can solve for C, no? And then we can see what happens. But, all right, anyway, so we know this, so let's see. We need to go to the tables for what substance? Ammonia, so Again, I ask you to bring the tables. So, all right, I'm going to go big here because I don't want to waste too much time. So which one are the tables for ammonia? 13? Okay, otherwise I will go to the, what is this one, 5, come on, 13, okay, I trust you, I'll go here. Okay, 9. This is refrigerant 134A, 12E. Okay, for ammonia. So here we have table A, 13E. So this is for English units, that's not the one who we want. We want the one with the, so page down, this 113. Okay, so temperature for ammonia, liquid vapor, this is what we're looking for. So a minus 20 over here, all right, would be this line over here. Okay, so from table A13 at T equal minus 20 degrees Celsius. Let's see, what do we have? I don't know what is all the information we're going to need, but okay, so let's say P1 should be equal to what? 1.9019 bar, no? Okay. Next, what do we have? V fluid, V gas. Which one needs to be higher, the V gas or the V fluid? What takes more volume, gas or liquid? Gas. So let me be right before the one of the gas. So the gas is 0.6233 cubic meters per kilogram, no? So what would be the value for the one of the fluid then? Is 1.5038 10 to the 3 or 10 to the minus 3? 10 to the minus 3. Okay, so I don't know if we're going to need more information, but if we need more information, we can come back. I think we're going to need all these UF and UG. So, I mean, let's write it down now, just in case we need it. If not, it's fine. So U sub F is equal to what? 88.40. U sub G. Okay, I was going to ask you, what has more energy? Liquid vapor or gas? Gas, no? So you see the numbers should be higher. So 1299.23. Okay? I think that's all we're going to need over here. Even though, just to check something, okay? I'm just going to add it here. Right? H sub F is 88.6H. A sub G is 1417.79. Oops, sorry guys. Okay, I was writing all this stuff, but I needed to see the table, so I just wrote all that information there, okay? That's why I asked you to bring the tables, no? Again, guys, I know I'm not trying to scare you or anything, but if you don't practice using the tables, it's like doing the free shot in basketball, no? You are taking a gamble. Okay? So in order to know how to use the tables, you need to practice. Just saying, okay? Yes?
What's the power on U sub F?
What is the what?
Like the power, it says times 10 to the negative 3.
10 to negative 3, yes.
Why is it?
You see on top of the table the part times 10 to the 3, no?
Right.
So what it means is that they have pre-multiplied that value by 10 to the 3.
Oh, okay.
Yeah, it's tricky. That's what I told you before. The way to remember this, if you need to multiply by 3 or 10 to minus 3, is to understand what takes more volume. Gas, a substance in the gas state or in the liquid state.
Okay, makes sense.
That makes sense? Yeah, it's tricky. I agree with you, okay? But all right, so now that we know VF and V fluid, how can we find V1? So do you remember this also that page where you have the two figures, PV and TV diagram, that has on the first side like 3 or 4 relations, no? One of them is what? V1 will be equal to what? V fluid plus X1 V gas minus V fluid. Yeah? Remember that page? Okay? So that's one of the pages you can also take to the exam, so you don't need to memorize this. Okay? I'm never going to ask you to memorize something, even though I hope you will remember that expression, okay? After using it. So now V1, if we do the numerical application, should be equal to what? So we have V fluid is 1.5038 10 to the minus 3 plus X1 is so 0.25 of, I mean, is that relation correct? Is it V fluid? Yes, no?
Yeah.
Did you check it? And then we have V gas is 0.6233 minus 1.5038 10 to the minus 3. So if you do the calculation, what do you find for V1? I don't know. So I could look at the solutions, but again, to me, solution is not what's important, is the process, no? So I guess you're gonna get 1.6, something like that. 0.16 something. 0.16. Man, I cannot be that accurate. I'll be lucky then. I need to play lottery then today. Okay, 0.156, 1.157. Okay. I mean, everything I did is just, this value is very small. The thing I did is divide 6 by 4, okay? These values are very small, so I was neglecting them. The only thing I did is this is 1/4 of 0.6. Okay, that's why I took it that value. So anyway, we have this. So now in this figure, if we want to be very accurate in this figure, we wanted to add values. So what was P1 over here? 1.9019. Now we know P2. Oops. So what is the state at 2 now? How can we find what is the state at 2? So we know the temperature. Over here. We know the temperature and we know the pressure, no? Okay? So if we go to the figure, let's say we go to the figure of temperature. So we go to 20. So what is the temperature at 20 here? What should be the pressure? 8.5762, no? So that means that if we look at this figure, the pressure corresponding to this line over here should be what? 8.5762. But P2, oh, what are the units for that? Sorry? Bar. So we need to be careful. We need to change that stuff. So 8.5762 bars. Yeah, so that will be, okay. So let's do one thing over here. So, all right, so let's say P2, we know P2 is equal to what? To 0.6 megapascals, no? Yeah? Okay, what was the relation? 1 bar was equal to how many kilopascal? I think it's about, what is it, 1.015, something like that? Check the relation. What is the relation between bars and kilopascal? Is it 1.015? I mean, you have that page, guys, with the units. I don't have it, so what is the relation between bars and kilopascals? One point?
No, 0.1 megapascal.
So 0.1 megapascals? Is it on top of the chart over here?
Yeah.
Okay, good. So then that's good then. Okay, so 1 bar is 0.1 megapascals. So that means that so this will be how many bars then? What do you mean 0.8? It's 0.6 over here, no?
Yeah.
Oh, so we have, so 1 bar is 0.1 megapascals. So 0.6 megapascal would be how many bars? 6 bars, no? Was like, why is it just 6? So 6 bars. So what does that mean over here then? If we go to the figure, where are we then? We know this is t equal to 20, but we are at P2 equal to, let's say here, six bar, no? So what does that mean about 0.2? Where is 0.2 going to be? On what region is 0.2 going to be? On the superheated or gas region.
What
Yes?
is the pressure for 8 something? 8 point for 20 degrees of
8.5762 bars.
So converting that to megapascal, how are we getting?
Yeah, but this is in bars. All this one we're doing this in bars. P1 was 1.9 bars, no?
Yeah.
So then this one, for here the saturation pressure is 8.5762, but the actual pressure they give us is 6 bars. So it means you are under this one, no?
Okay, yeah.
So in order to be at the same temperature, what you need to do, you can only cut the curve over here, no? Going down. So that means we are on the gas or superheated region. Now, what do we know about the relation between P1 and P2 is linear. Okay? So we plot it. We'll plot something like this. Okay? And now over here we'll have B2. I mean, you see, guys, that even if they ask you to do the figure, you need to do the figure, no? There is no way to solve the problem without the figure. Okay. So now that we know that, yes, go ahead.
Yeah. How do you know at 6 bar? How do you know that it's superheated and that it's not still a mixture?
Okay, because this line over here, these lines of constant temperature, no? Okay, so between this point here and this point here is going to be constant pressure.
Between 20 degrees and -20.
Between this point here and this point here, pressure is 8.5762, no? Yeah? So if you want to, so if the pressure was higher than 8.5762, what would be the state? It will have to be along this line, no? It will be liquid, but since it's smaller, what is the only solution? Is that it's along this part of the line. Is that clear? Okay, there's no bad questions. Probably more than one person have the same question, okay? So don't be scared or shy to ask any question. This is the time to study with me. Okay, so I'll stop as much as I have to. All right, so now they tell us that the relation between P1 and P2 is linear. So, but before doing that, can we find V2? Now we know that in order to find V2, we need to go to the tables of superheated ammonia, no? Okay, so what will be that table? So it's probably, is it table A15? Okay, I trust you, but again, let me magnify this. So table A14, this is still liquid vapor. 815, superheated ammonia. Okay? We have to deal with what pressure? 6 bars. Hopefully we have 6 bars. We don't have to do create interpolations because I don't feel like doing any interpolation. So 6 bars. And we have the temperature of 20, no? So this will be the values. Okay? So table A15. Again, I write it down, then I'll show you on the document. So we have V2, so table A15 at P equals 6 bars and T equals 20 degrees Celsius. What do we have? We have V2 equal to 0.22155. U2 equal to 1347.62 and H2 equal to 1480.55. That's interesting now. So. Okay, here I have a little doubt now. So why did they tell us in the program that the relation between the pressure is linear? Because I'm pretty sure that if we know P1 and we know V1 and we find C, that C will be different than from the P2, V2, no? Yeah? It could be the same, but that would be to be very lucky, no? So linear is just a linear curve. So P2 was given to us, no?
Yeah.
And the temperature is also given to us. Can you check very quick what is the difference between the C if you do C equals to P1 divided by V1? But we probably need to change the, do it with P2, with the megapascals. Okay, what is this problem number 35? Let me check very quick. Let's see what they did on the solution manual, because that's a little bit unclear to me. Yeah, I'm gonna go check real quick. Okay, so we are good. All right, that's very good, but that doesn't mean that it's the same thing. Okay, so we got the same figure, that's fine. So they do it graphically, but that's not the way to do it. What do you get for one and the other? Are they far away from each other or close? All right, I see exactly what is need to be done, but they do it graphically. So, do you find a big difference or no?
I don't think I'm doing it right.
Yeah.
So you get 12 and I get 3.
I think I did it wrong. I'm dividing. 1, 2, 1, 3. We're finding C.
Okay. So graphically, yeah, it's very easy to know what they're doing, but
I got C, it was like 63.49.
for both cases,
I mean, you only do,
you did it only with P2.
I just did like P2 minus P1 over P2 minus P1.
V2 minus, okay, and do it, okay, so we can do it that way, that would be even, okay. We're gonna do it that way, I like that way, all right? So basically, all right, so knowing that P varies linearly, okay? So I like the way he did it. So we're gonna have 1 and 2, no? So the change in height that will be equal to what? You want the, let's say this one, let's say beta here will be tangent beta will be the slope, no? Yeah? So it will be basically C. So this will be equal to what? P2 minus P1 times V2 minus P1. This will be the slope, no? So the constant, C equal to slope. So we can have over here. So then we have here slope will be equal to what? So P2 we had, I think the difference would be the same either if you use bars or megapascals.
Yeah.
So difference will it be the same or no? Yeah.
Yeah.
Eh? So then make sure we use megapascals then. If we use megapascals, so what would be P2 in megapascal was 0.6. What would be P1 in megapascals? 0.19. 0.19019 to be accurate, but 0.19 is plenty. And then V2 is, we just calculated.
0.22.
Yeah, V2 is over here. Point 22155 minus V1 we found to be equal to 0.157. So what do you find for the slope? 6.39.
349.
6.39 is enough for me.
Will be
3, 4,
349.
35. Okay. 6.35. So basically, I mean, this is just math, but let's see. The function p of v is equal to what? Will be equal to p1 plus cv, no? So will be equal to p1 plus 6.35 v. Is that correct? So now if I do p1 plus 6.35 times v2 minus v1, I should get the value for p2, no? Okay. So basically, this is the equation. So 53, 55. Okay, so why am I doing all this stuff? You could have done it graphically as it did on the solution. But why am I doing all this stuff? Because we know that the work, the general definition of work is equal to what? Minus the integral of minus p dv, no? So in this case, what is p for us? p1 plus 6.35 v, no? So if we substitute, we're going to get minus integral of p1 plus 6.35 v dv, and we need to integrate this between what? v1 and v2. So if we do the integral of this, we're going to get minus p1 v no, because this one will be p1 v, no? Plus p1 between, let me break it in two so it's clear, v1 v2 no, plus, no, minus 6.35 v2 over 2, no? Between v1 and v2. So if you do this calculation, what do you get? And be careful with the units because P's are in megapascals, no? Yes, so P's in megapascals, so make sure at the end you give me the result in kilojoules. So you guys, if you don't practice in class, it's going to be hard, no? I'll let you do the numerical application on your own. So P1 will be what? Let's just do values of P1. What would be P1? P1 was equal to, see the figure, 0.1909 megapascals, no? So that will be equal to what? 190.19 kilopascals, no? Yeah? You multiply by 3, no?
Yeah.
Mega is 10 to the 6. So will be, so 0.19, 123, 190.19 kilopascals. And the V's will be units of cubic meters per kilogram. So that should give you kilojoules. Okay, and P2 should be, I think, 600 kilopascals, no? Yeah? Yeah, don't do the calculation in bars, otherwise you're gonna have the units wrong. So guys, again, I told you need to bring tables, calculator to class, no? To practice. I could just go and look at the solution, but it's not part of the purpose. The purpose is that we practice a little bit in class. So just go to the solution and tell you this is equal to this, no? So what is this equal to? Guys, I'm telling you something. Again, I'm not trying to scare anyone, but if you don't practice in class, trust me, the day of the exam is not going to be pretty. Yes?
You have a date in mind for that exam?
Next week.
Same
Yes, what I'm thinking is probably homework due on Tuesday. Tuesday we look at the homework and we do like a review, and Thursday you have the exam. Okay? So what is this value? I'm not going to do it for you, so you are just wasting your time. Okay, I can check quick, see if you get something similar. Oh, they do the average here. 1.91 bar. So what do they get for the energy? They don't even tell you. Oh, yeah. So what do you get? Okay, so if you cannot do it, I'm not.
Oh, you got like 11.9.
Okay, that's fine. They had 12.75, so 11.9 is fine with our 11.9. Can somebody? Okay, you get 12 point what? I mean, why do we get? You see, guys, what I tell about using your calculators? Huh? Even those little things can be different. So, what about having somebody double checking this one? We have 11.9 and 12 point something so far. I mean, you know, the day of the exam, somebody's not going to do it for you. Let me try something here. Okay, that will work. I mean, you realize that if the day of the exam you spend that much time in that calculation, you're not going to get done, no? I mean, 12.19? Okay. So minus 12.2, is that okay? All right? Okay. So now that we have this, what can we say? So applying first principle of thermodynamics will be what? Q plus work equal to what? change in internal energy, no? So in this case, so we have what? So Q will be equal to what? Change in internal energy minus work. So will be equal to M U2 minus U1 minus 12.2 kilojoules. Okay? Oh, I forgot to do something. We also need to multiply this one by M because this is, we didn't multiply this one by M, no? So be careful here with something. Maybe I did something wrong here. What are the units for this one? Kilograms per, so kilojoules per kilograms, no? So or W will be equal to minus 6.1 kilojoules, no? Because this is really, so let me change this. This is, sorry for that guys, but this is work per unit mass, all right? And the mass is 0.5 kilograms, so will be half. So this will be here, minus 6.1. All right, so over here, in order to do that calculation, we know M is 0.5. We know what is U2. U2 will be equal, so we know M equals 0.5. U2 is equal to what? 1,347.62. Okay, the work, we already put it over there, is equal to minus 6.1 kilojoules. Now, what is U1? We should have calculated that one, but what would be U1? In order to find U1, what do we need to do? The same thing we did here for V1, no? We do the same thing. So we have U1 will be equal to UF plus X1 U gas minus UF. I'll let you do that calculation. Where UF and UG are equal to what? Whatever we had at the beginning. 88.4 and 1299.23. So what do you get for U1?
39.1. Oh, 391.
Yeah, I get 391 as well.
391.1, okay, and this should be kilojoules per kilogram, okay? So now, substituting to this equation here, so and Q will be equal to what? Will be equal to 0.5 times 391.1 minus, oops, I did a mistake, minus 1347.62 minus 391.1 minus 6.1. So that will give you what? 472.2? Okay. Okay, so now let me just show you something. See if it works good or not. Okay, that's what I'm doing off on the other page. So I'm going to do it in blue. So here, note. '57. So again, if I go back to the class notes of today, what is the difference between U and H? What is H is internal energy plus work done by the pressure, no? Okay? So in this problem over here, what do we have? We have internal energy, no? Plus work done by the pressure. Correct? So this equation here, if you think about it, all right, when we had the first law, work plus this equal change in internal energy, no? What do we have? This is equal to what? Q minus PV equals delta U. So we had Q equal to delta U plus PV, and this should be equal to what? Delta H, no? So maybe we could have said what? That the total change in heat will be equal to what? M, yes, delta H. M H2 minus H1. But again, I'd rather you doing it the other way, okay? So if we check the result doing this way, what is H2? So maybe I did not take it, but
1,480.
did we write it down from table A15? Yes, so let me see if I find it so I can show it to you. So from table A15 here is 400, so 1480.55, no? So 1480.55, and what would be H1? For H1, we need to do the same thing as before, no? This will be equal to what? H sub F plus X sub 1, Xg minus X sub F. And what do you take for H sub F and H sub G? The one from table A13. H sub F equal to 88.68. H sub G equal to 14.77. So what do you get for H sub 1? 729.
708.8.
So 708.8. Somebody double checks that. I mean, it will be 88 plus, let's see, 600, a quarter, 200. Yeah, that sounds about right. How did you get?
708.89.
708? 708.89? I mean, 708.89. Guys, I mean, if you don't do it, again, so at the end we could say that Q will be equal to what? 0.5 times H2 equal to 1480 minus 708.89. So let's say that's about what? 760 divided by 2. What was the other result we got? 472. What do we get this way?
That one's 385.8.
385.8. Okay. Now you see that this is not an exact science, no? So, all right, so let me ask you a question here, all right? Since we don't have that much time. Okay, so let's summarize this. So let's see, 54, 55, 56, 57, okay? So So we have to solve this problem over here. Okay? So what is the assumption we are making? That is linear, no? Okay? So if you assume it's linear, we did other calculation, we did the figure, and then we, in order to find the work, we did the assumption that this is linear, so we ended up taking this expression here. Okay? So taking that assumption, we found that the amount of heat was equal to 472.2. All right? Now, which generally they don't do it this way, but it's correct. When I did it this way, did we do any assumption about the pressure? So which one do you think should be more accurate? Probably this one, no? But again, thermodynamics, like engineering, is not an exact science, no? So you see, like, for example, on the exam, you do this problem. Either on one way or the other, you're going to get different result. But that doesn't mean that what you have done is wrong. Yeah? Okay? So basically, can you say that this was a very good assumption or is not a very good assumption? It's not a very good assumption for this case, no? Okay? But again, generally, they don't want you to do this, okay? Yes, go ahead.
Which HG value did you use? It says 1480. What table did you use?
No, that one comes from table A15.
Okay.
Yeah, that one should come from table A15 here at superheated.
Okay.
At 6 bar and T20. H2 was 1480.55. Okay? So, guys, start working on the homework. Okay, I will add some problems. So basically what's going to happen is this. Thursday, I might do a couple more problems. Then Tuesday you have a homework due. And Thursday you have the exam of next week, okay? What were your questions?
Is the homework posted on Hands?
Yes. No? Hold on 1 second. Homework 2, this one, let's see. I already posted some problems. Okay? So I'm going to add some more problems.